Hi everyone, welcome to our 3 p.m. press workshop. The Sentinel-5P satellite goes beyond expectations to monitor air quality. Our speakers today are Claus Zehner from the European Space Agency, Barry Leffer from NASA, Pepijn Viefkind from the Royal Netherlands Meteorological Institute, and Diego Loyola from the German Aerospace Center.
Thanks. As I've already been introduced, I guess I can skip the first slide. Sentinel-5 Precursor is the first atmospheric Sentinel mission. It's a Copernicus mission. So a few words about the Copernicus program. Copernicus is a European Earth observation program with the goal to establish in Europe a capability to be able to respond to global needs, for example, to manage the environment, to be able to react to climate change, and also to ensure civil security. ESA is working here close together with the European Union. The program is led by the European Union. What ESA is doing here, we are responsible for setting up the space segment for the Copernicus program, and the space segment, these are the Sentinel satellites. So far, ESA has launched 7 satellites since the year 2014, and all of them are really working well. So already this alone, on its own, is a success story. These satellites, they are providing information to services, operational services that are led by the European Union. And these services, they are using the satellite data, converting these measurements into information that is really being needed by end users, for example, in the Europe environmental protection agencies. So Sentinel-5 Precursor is an atmospheric mission providing atmospheric composition data that can be used for air quality and climate monitoring. On this satellite, there's one instrument. It's called TROPOMI. TROPOMI stands for Tropospheric Monitoring Instrument and has been co-funded by the Netherlands and ESA. It has been launched during October 13, 2017. And what's the big advantage of this instrument as compared to previous satellite instruments is its enhanced radiometric sensitivity, so providing information with higher accuracy, but also the spatial resolution of the data. And showing this on the spatial resolution, what you see here is intercomparison between a TROPOMI to OMI data. OMI stands for Ozone Monitoring Instrument, Dutch contribution to the NASA U.S.A. satellite. But you see here, by having 7 times 3.5 kilometers as compared to 13 times 23, looking at air pollution from space, you really see an enhancement of the information content. And again, what is important with TROPOMI, you get global coverage within 1 day. Coming now to the products that are being provided, or the information that is being provided by Sentinel-5P to the public, to the users. So far, we have released species that are really important for air quality monitoring, like nitrogen dioxide, ozone, formaldehyde, carbon dioxide, and sulfur dioxide. Methane, a greenhouse gas, has still not been released. We are planning to release it early 2019. We are working on it. Now, coming to the data policy, how can you get the data? Sentinel-5P is a Sentinel belonging to the Copernicus program. As such, the Copernicus data policy is applicable, and this data policy is completely open. So you can download the data, you can, for example, you can redistribute the data, you can generate your own higher level products based on lower level products. So the key message here, the data are available completely for free, and you can download them at these sites. Here, an example showing you how you can use TROPOMI measurements on a global scale. Here, example, this is a monthly average over April 2018, and you can intercompare air pollution emissions of nitrogen dioxide in India to the ones in China. This is just one example how, for example, Greenpeace is using the TROPOMI measurements. What they are doing, they are overlaying TROPOMI nitrogen dioxide over a map in Europe where you have information, where you have coal-fired power plants. These are these black dots. and they are providing this information to the public. As I've mentioned before, a key issue for this Copernicus program is that satellite data are being used and then converted into information that is useful for the end users like environmental protection agencies, but also people on the street. And what you see here in this chart, the Copernicus Atmospheric Monitoring Service that is operated by ECMWF is using our near real-time level 2 products, including it into a data assimilation system that enables forecasting of air quality information. And this information can then be used by end users, for example, people who have problems with their health, their lungs or heart, via here a cellular phone, in order to reduce their exposure to air pollution. Studies have shown that in Europe we have about 400,000 premature deaths based on air pollution. As mentioned before, we are flying Sentinel-5P behind SOMI MPP. Why we are doing this? First, this provides the possibility to use Viirs cloud information in the tropomi methane retrieval, allowing the selection of cloud-free pixels for which we can do high accurate retrieval. Having the satellites so close to each other, it's also easy to intercompare measurements from the different instruments, and we use this in order to validate the tropomi measurements using SOMI MPP data, and also you have the possibility for synergistic data exploitation. Here, a point source measurement of sulfur dioxide volcanic emissions over Indonesia during 2017. And these data have been validated, intercompared to data coming from the ARMS instrument, also sulfur dioxide, that is on SOMI NPP. And this line is indicating in case these black dots are on the line, there's a very good agreement. And this is just one way how to show how this intercomparison works and how we are cooperating with our colleagues here in the US, NASA, and NOAA. And I'm stopping here. Thanks for your attention.
Hello, my name is Barry Leffer. I work at NASA headquarters. I'm the program manager for the Tropospheric Composition program, and NASA is very excited about TROPOMI. We have a long history of a partnership with ESA and the European Space Agencies going back over 20 years. They were part of the original Earth Observing System satellites that went up, and several European instruments ended up on the NASA satellites, OMI being one of them. It's a partnership with our Dutch colleagues. So OMI's been up for, is it 18 years or 17? 14. I'm thinking of I'm thinking of Terra, but OMI's on the Aura spacecraft. It's over 14 years, coming on 15 years. The idea of there's several other satellites flying with Aura in what NASA calls the A train, and in that constellation of satellites, we learned that we could have multiple instruments looking at the same part of the Earth minutes apart, and how that was a way of having multiple satellites, instead of putting all the satellites on all the instruments on one giant satellite, having the flexibility to add additional satellites to the constellation would give us flexibility and also give us the ability to update instruments over time. And so Claus mentioned this partnership between SOMI NPP and the TROPOMI Sentinel-5P satellite. And what this figure is showing is that they have a mean local transit time over the equator of only 5 minutes apart. And this allows all the measurements on the SOMI MPP satellite to work together with all the wonderful measurements on the Sentinel-5P satellite. And so we are looking forward to doing some joint retrievals. Claus mentioned the Viirs instrument. This is a lot like MODIS you might be familiar with, where it's a hyperspectral instrument that we're able to look at aerosol properties, but also look at the land surface and clouds. And so there's also a tropomi-like instrument on SUMI MPP, but it's much coarser spatial resolution. And so both of us will benefit from this close partnership. What I'm showing here is the swath of Viirs first in line and tropomi 5 minutes behind it. So you can see how complementary the field of view of these two instruments are and how we can easily leverage this close, small separation between these two platforms. And I'd be happy to take more questions later regarding this partnership between NASA and ESA.
So, good afternoon. My name is Pepijn Veefkind. I'm from KNMI in the Netherlands. And what I'm going to do in this presentation, I'm going to show some of the results that we already have with the tropomi instrument on several of the trace gases that we are measuring. And I'm going to start off with this global map of NO2. So NO2 is a pollutant. And it's produced when you burn stuff, whether it's, for example, power plants or whether it's wildfires. What NO2 has is it has a very short lifetime of only a day, so the pollutants do not travel that far, so you can really look at where things are emitted. And the very nice thing about a satellite instrument is that with one instrument, you sample the entire Earth in 1 day. And that really gives you a way of comparing the different areas in the world and their concentration in NO2. So we can really look at the different hotspots. So I'm showing here 3, North America, Europe, and East Asia. And you see all kind of features that happen on the ground in this picture. Let's see, this is... So you see here, for example, Europe. I'm living right there in that red hotspot that you see, which is an area where there are a lot of people, and therefore there's also quite high NO2 pollution. But you also see, for example, these ship tracks that go through the Mediterranean, caused by these large ships that go into the harbor region of Rotterdam and Antwerp. In China, you of course see the major cities. So you see here the area around Beijing, and then you have Korea with Seoul, and then here is Japan. And you see there's a lot of more detailed information and more detailed information that we ever had on these distributions within the tropomi data. So what we can do here, you see the zoom in on North America. You can see the major cities, so it's New York and Chicago, but also and LA, but also all the smaller emission regions. And we can now, with the tropomi data, zoom into this even further. So I here zoom into the East Coast, showing there New York and Philadelphia and Baltimore, Washington area. So you can zoom even further, and then you go to the city level. So you can really go from the global view, the total Earth, zoom all the way into the urban regions. And this is a zoom in over New York that I did. This is a monthly average in one of the months this summer, and you can really see the differences between the area over Newark, which has the maximum value actually in this month, and then here this is the Manhattan and the Bronx region with more the city pollutants from the traffic, whereas this is more the airport and the harbor region. So this is where tropomi is really intended for, really to look into the urban areas and to compare the concentrations within the larger cities, as you can see here over New York. Now we can zoom out again. Now I'm switching from NO2 to carbon monoxide. And carbon monoxide is produced when you have incomplete burning. So especially when you have wildfires, you're going to produce a whole lot of carbon monoxide. And you see a movie, so each frame that you see is one day, and this is in August. And you see the major biomass burning regions in Africa and over South America. But what you also see is in the northern hemisphere, you see a lot of CO being produced in the United States and Canada from the wildfires that were very heavy this year. And because CO lives longer, it travels much further away than for example, NO2. And you can trace these plumes that, from the source regions and see how they go over the entire hemisphere. And this is really a new measurement compared with what we had, for example, with OMI, because we did not have that spectral channel on the OMI instrument, where we do have it on the TROP-OMI instrument. And of course, we can also zoom into this for the very recent dramatic things that happened in California, in the city of Paradise. This is a picture I took from the Washington Post website, where you can see the very big plume and the very intense fire that happened on November the 8th, just a little over a month ago. And here I'm showing the Viirs image. So this is from the MPP, the NASA satellite that flies just 5 minutes ahead of us. And here, this is the region where the fires are, and here you see this big plume coming from it. And this complete plume, which is several hundred kilometers, was formed just in one day. That's because we know that the previous day it just wasn't there. So it's a very big plume that formed very rapidly. So now we can overlay the NO2 data on top of that. So here you see very high concentrations of NO2 in the region of the burning, which is telling us also that this fire is very hot, and you produce a lot of NO2 in that plume. Also, if you look at here, you see high concentrations over LA. That's more the pollution from the city, whereas this is from the biomass, from the wildfire. And because we measure different species on TROP-OMI, we can also say something about the origin. So here I'm showing this NO2. This is the same image as I had in the previous slide, with the high concentrations over the wildfires and the high concentrations over LA. But now if you look into CO, for example, CO is produced a lot in the wildfires because it's incomplete burning, whereas it's not producing so much CO over the city, which is more controlled burning. So this is really, really powerful that you can combine these different products to tell what's going on at the surface. And that we can do this, of course, as I showed, globally. Now, some slides about the upcoming methane products. So methane is primarily of interest for climate. It's the second most important greenhouse gas after anthropogenic greenhouse gas after CO2. And here, this is really where this virtual platform where we combine MPP with S5P is intended for. You see here, this is a cloud masking. This is an orbit over the US. And you see here, this is the cloud mask produced by the Viirs Instrument. Blue means it's identified as clear, and then you go all the way up to cloudy. And for methane, it's essential that we measure only in the cloud-free regions because these measurements have to be very accurate, and we have to ensure that we do not have any cloudiness in them. And here you see how we use it. Now it's the methane data overlaid on it, and we use this cloud mask from Viirs that flies just 5 minutes ahead of us to point us at the right targets where we can do our retrievals. So this is a really good way and powerful way of using these platforms together. And well, my final slide here is on these orbits of methane. We then construct the global map again, and this product is something that the community is looking forward to, and this is something that we plan to release in February of next year. And this is a very important measurement for climate. And my final slide is just where you can find some more information and some contact information of myself. Thank you.
So, good afternoon also from my name. My name is Loyola. I'm working at the German Aerospace Center. I will present now some work that we are doing together with colleagues from the Royal Belgian Aerospace Institute. So you will see some additional results that we are having with tropomy. First on clouds. On the left side, you see the Viirs SPP images. That's what everyone knows also from the weather forecast and so on. On the left side, you see tropomy, the cloud top height, and this image shows very nice also the complementary of having these two systems flying together, because on one side we cover different parts of the spectral range that give us also additional information, and we can also combine the different spatial resolutions. For this particular case, that was the Typhoon U2 in Philippines last October, there was also a fly through the eye from CloudSat, and CloudSat gives you a very, very detailed information about the location of these clouds. And it helps us also to validate our products, because we can clearly see with CloudSat that close to the typhoon, the altitude of these clouds are around 10 kilometers. We clearly also see now the eye of the typhoon, also with tropomy data, and the values are also in the range that we are retrieving. And for the first time using this kind of spectrometers, because we have more than 4,000 spectral lines. In previous missions, we hadn't this very nice resolution, but now for the first time, we also, for example, can see the eye of such a typhoon. Now let's move to the trace gases itself. The first one is the ozone. As you know, there are two types of ozone. Let's say the good ozone, the one that helps us or basically stops all the UV radiation. And that's very important for all living creatures here on the Earth. What you see here is an animation of using just S5P data for 1 month. So we can see how the ozone hole is closing, as happens every year. What's nice here is really the detail of information. We didn't have this detail on previous missions. And also, for the first time, we can create this kind of images just using the satellite data without the need of further interpolation or even using some assimilation systems. On the other side, ozone has a very high requirements on the accuracy. Why? Because we really want to understand what's coming from the anthropogenic contribution and what's natural variability. So that means that the accuracy required for this product is in the order of 1%. That's quite high. And we are happy that already now, just 1 year after launch, we have reached this accuracy. And that's why, as Claus mentioned, this data has been assimilated, for example, in the CAM system. But with tropomy, we can also retrieve the tropospheric ozone. That's the ozone at the surface, the ozone that also produces problems to all living creatures, not only animals, but also the agriculture is affected. With tropomy, we can really detect also this information very close to the surface. This animation shows you how dynamic this information is. That's an animation covering the time period from March to July. Let's now continue with another trace gas, that's formaldehyde. That's so-called a precursor, because that's one of the gases that creates this tropospheric ozone. This picture shows you 1 year of data on a global scale. You can really see the different regions, how formaldehyde is being created. If we zoom into the US, now just on average over the summer period, so from July to August, you clearly identify the two main sources for this particular event in this year. On one side are the California fires that you saw also in the previous presentations. And on the other coast, you see also the biogenic emissions, so that's natural emissions. Let's move now to the SO2, that's sulfur dioxide. The main anthropogenic emissions can be separated in two sources. in this part of the world, the main sources are related to the power plants. That's the red dots. And on the blue, you see also the oil and gas. And if you really move, sorry, the wrong direction, if you can really detect all these sources, we can measure this really basically on a daily basis. We can identify exactly where these sources are coming from, and also we can detect some sources that are not yet on the registers, let's say. Another example of using these two satellites together, what you see here is the SO2, the sulfur dioxide coming from the volcanic eruption on Hawaii from last June. You see on the Viirs images, you see the lava flow on the right side, but also you really see very nice the volcanic smoke. On top of that, we can retrieve the sulfur dioxide. That's also very, very important source of information from Tropomi. And as you can see, they match almost perfectly. So we have different kinds of information coming from different sensors, but we can combine this information. And for this particular case, but on May, thanks to the powerful spatial resolution of Tropomi, we can not only see that it's coming from the volcan, but we can distinguish the two sources. So in this case, there is the main volcan, but there was also a fissure that started a few kilometers apart. And only with Tropomi, we can really detect or see that it's coming from two different sources. And that's also important to really quantify the contamination from, in this case, for sulfur dioxide. Finally, I would like to show you another kind of applications. It's also for volcanic eruptions, but for aviation control. Maybe some of you remember in 2010 there was a very big volcanic eruption from Iceland that stopped basically all the air traffic in Europe. It has also several consequences on financial aspects. At that time, we didn't have so powerful sensors, so that's why the complete European space was closed. Now with Tropomi, you see this example now in Sierra Negra in Ecuador, we can really detect exactly where regions are affected, and then you don't need to close the full aerospace, you can only close the regions that are affected. On the left side, you see the SO2, but of course for aviation control, they only need to know where it's coming, but also the altitude, because the airplanes are flying over there. And what you see on the right side is just one product that's not yet operational, but we can retrieve also the altitude of the layer height, so you can provide this information for aviation control. The last slide, you can have some information where to access the data. There are also some web pages where you can download images and also make zooms to see different examples, like for volcanic eruptions, and also the contact information. Thank you very much.
Thank you. We will now open it up to questions from reporters in the room. Please state your name and affiliation. Are there any questions from reporters in the room?
Harvey Lyford, freelance. Why Precursor?
It's on.
It's on? Okay. Because there are follow-on instruments within the framework of Copernicus Sentinel-5 and Sentinel-4. So it's a precursor for these Copernicus missions. At the same time, it's also an extension of previous missions like OMI and GOME or Skirmaki.
Are there any other questions from reporters in the room?
My name is Stuart Wills. I'm from Optics and Photonics News, and I was just wondering if you could describe a bit more what the instrument itself, what it's measuring and how, and maybe contrast it with the instrument that was mentioned on SWOMI NPP that is similar but lower resolution.
Okay. Yeah. So the Tropomi instrument is a spectrometer which actually has 4 bands. So it measures in the UV, in the visible up to the green, 500 nanometers. And there's a near-infrared band and a shortwave infrared band. And all these 4 bands, they are equipped with a 2-dimensional detector where one of the dimensions is used for the spectral information, and the other is used for the spatial information across our track. measurement method was also used for the OMI instrument, and is also used in the OMS instrument. What makes the high spatial resolution of the TROP-OMI instrument is that the instrument itself is much larger, so because we have to have a very high signal-to-noise ratio on our spectra, we built this instrument such that it has a much larger telescope, and we can measure a whole lot more light and at very high signal-to-noise ratios. For comparison, the OMI instrument was quite small. It was 40 kilograms, whereas the TROP-OMI instrument is way larger and weighs more than 200 kilograms. So it's a really, on the one hand, it's getting more photons, having a bigger aperture, and on the other hand, of course, the parts that went into it also have newer techniques, because OMI, of course, was built more than 15 years ago, and TROP-OMI is using the latest techniques.
I was just going to add, these are CCD detectors for in the UV visible, and there's a grating to do the wavelength separation.
Right.
Are there any other questions from reporters in the room? Are there any questions on the chat? No? Okay, great. That concludes our press workshop. Thank you very much.